how to rotate molecules in order to obtain the stereochemistry. There are two ways to go about this. So one, with this specific molecule, we actually don't need to rotate the molecule. So we'll do this method first. We want to order the priorities of the substituents attached to the essential carbon. The priorities are determined by molecular weight. The higher the molecular weight, the higher the priority. So chlorine is the heaviest. It's going to get priority 1. Oxygen would get priority 2, and methyl will get priority 3. We don't need to label the last priority. We can therefore draw an arrow. So if we were to redraw this molecule, just so that we have it. So we have it labeled 1, 2, and 3. Now we can draw an arrow from priority 1 to priority 2, priority 2 to priority 3, and priority 3 to priority 1. We see that we get a clockwise fashion of rotation. A clockwise fashion is denoted as R, whereas, however, we have to note that the lowest priority group, which is hydrogen, is on the wedge. And recall, the wedge means to the front, whereas the dash means to the back. And so, because our lowest priority group is to the front, we need to invert the stereochemistry. So, inversion. And so we would actually get the correct answer to be S, which is counterclockwise. Because when assigning stereochemistry, the lowest priority group must be to the back of the molecule. The other way to attempt this is to actually rotate the molecule so that the lowest priority group is in the back. We can do that by simply grabbing one molecule, or one substituent rather, that's in the plane and holding it still. We then twist the molecule so that the substituents rearrange. If we were to do that here, then say we grab hydroxyl. Let's rotate the molecules and see what happens, where they go. So if I hold it, the hydrogen would go to the chlorine. It's a terrible color, actually. Let's do... So the hydrogen goes to where the methyl is. The methyl would take where the chlorine is, and the chlorine would go to where the hydrogen was. As a result, we would get a molecule that looks like this. So remember, hydrogen moved to the back on the dash, methyl moved to in the plane, and the chlorine moved to the front. Now, we can again assign the priorities 1, 2, 3, and if we do the arrow drawing from 1 to 2, 2 to 3, and 3 to 1, we get the S configuration. Just separate these. So those are the two approaches, and in the end we have the we came to the same conclusion. Okay. Now, what happens? We don't really use the rotation unless we actually need to. So a case where we might need to is if we had a molecule like this. Hold this page and have to avoid confusion. So if we had a molecule such as this, well, and our hydrogen's here. Our hydrogen is in the plane, and we need to rotate it so that the hydrogen is oriented to the back of the molecule. And I guess it's just helpful to note this is a methyl. If nothing's drawn there, then it's a methyl, it's a carbon. So what we do is, again, hold one of the molecules in the plane. Notice that we can't hold hydrogen because we want to rotate hydrogen to the back. So we're going to hold this R group, and we're going to twist it. As a result of twisting it, we would move the hydrogen to the position of the methyl to the position of the ethyl, and the ethyl to the position of the hydrogen. And that would result in a molecule that looks like this. Remember, this R group, it remains where it initially was because we held it constant, we held it still. So hydrogen came down to the dash, methyl moved over to the front, the ethyl moved to in the plane. So we'll just draw another line there. That's our ethyl. Now we can assign the stereochemistry just like we did before. And so we do 1, 2, 3. Oxygen is heaviest, then the ethyl, then the methyl. Again, we don't label the last one. And we draw the arrows from 1 to 2, from 2 to 3, from 3 to 1. We see that it is moving in a counterclockwise fashion, and so we denote this molecule to be in the S configuration.